Thank you very much, Dr. Claudia Ratti. So today I'll be talking about to you the equation of state based on lattice QCD. I'll talk about the expansion schemes and I'll discuss the critical point. Let me thank my advisor for guiding me through this time at University of Houston, and let me thank my committee for the support they have given me during my research. So I'm a graduate student, soon to finish from the nuclear theory group. And let me also thank the funding for the money they have given us that made this research possible. So in my outline, I'll give an introduction where I'll discuss the QCD phase diagram. I'll talk about the equation of state at zero chemical potential or at zero density. In the first part, I'll talk about the equation of state at finite chemical potential, and I'll discuss the expansion schemes that we use to push the result to finite chemical potential. The last three parts, basically this is much of my contribution. In the second part, I'll discuss the convergence properties of the T prime expansion scheme in the low and the high temperature regime. And in the third part, I'll show how we introduce the critical point into this T prime expansion scheme. And in the last part, I'll show how we generalized this T prime expansion scheme to give a four-dimensional equation of state. So stronger interacting matter, basically, so just 1 second. Okay, sorry for the technical difficulties. So stronger interacting matter basically is one of the four forces of nature that we have. We have the gravitational force, the electromagnetic force, the weak force, and the strong force. The strong force is interesting because it forms most of the visible matter that we see in our universe. And the theory that describes this force is what we call the quantum chromodynamics, which we always abbreviate as QCD. So the forces that the particles that experience this force are called quarks and gluons. So here I show you 6 flavors of quarks and gluons. So we have up, down, strange, charm, and top and bottom. And also we have the gluon that mediate the strong force. As in electromagnetism, we have a photon that mediates the electromagnetic force. In the strong force, we have the gluon that mediate that force. The question you can ask, where do we find these quarks and gluons? As I say that it forms most of the visible matter we see in our universe. If you look at an atom, inside it has these protons and neutrons. So protons and neutrons, when you break them inside, you have these fundamental particles which are called quarks and gluons. For example, proton, it has up, down, and these particles which have at least 3 quarks, we call them baryons. But also we have other particles that have 2 quarks. For example, a pion, it has down and up. So these ones have always a particle and an antiparticle, a quark and antiquark. These ones are called mesons. So all these particles, we call them hadrons. So the most interesting thing is what happens to these hadrons when you put them under extreme conditions. But before I talk to that, I'll talk about the coupling constant, which governs the interaction of these quarks and gluons inside these hadrons. So the coupling constant, it is called the constant, but as you see here, it is a function of energy. And when you plot it as a function of energy, we see that at low energy, it is strong. And when the energy increases, the coupling constant becomes weak and weak. So at low energy, we cannot do perturbation theory. So the system is non-perturbative. The way we treat it using non-perturbative methods like lattice QCD, as I will discuss. At high energy, the coupling constant is small. In that case, you can always do perturbation theory, and then you can always solve the QCD in these 2 limits. So if you look at these hadrons, which are baryons and mesons, baryons have 3 quarks, mesons have a quark and antiquark. When you put them under extreme conditions, for example, when you increase the temperature, you can show that these quarks and gluons basically melt to form a new state which we call the quark-gluon plasma, where these quarks and gluons are free, they are no longer confined in a state. in hadrons. But also this can be achieved by increasing the density. When you increase the density, you can still melt, or when you bombard them, you can melt them to form a new state, which is called the quark-gluon plasma. So we see that we have different states. We have the confined state, where quarks and gluons are confined to form these hadrons, and we have a different phase where these quarks and gluons are free, which we call asymptotic freedom. So this motivates, or these different phases can be captured in the QCD phase diagram, which is represented here as a function of temperature and baryon chemical potential. So the baryon chemical potential basically is the proxy of increasing the density. So at low temperature, we have the hadron gas, where we have these baryons and mesons, and at high temperature, we have quark-gluon plasma. So the goal is to understand this phase diagram, but what I can tell you, we don't know much about the QCD phase diagram. But what we know from lattice simulations, that at zero chemical potential, the transition from these hadrons, quark-gluon plasma, is a smooth transition. However, at finite chemical potential, lattice QCD suffer what we call the Fermi sign problem, or it is challenged by the Fermi sign problem. QCD effective models predict that when you go to finite chemical potential, the smooth crossover evolves into a line of first order phase transition with a critical point. The search for the critical point is at the core of both experiments and theory. So from experiments, we have experiments LHC, the Large Hadron Collider, that explore the low temperature region, as you can see here, at T equals to, at energies, which is about 2.76. And also we have the beam energy scan program that try to scan through this phase diagram. The hope is that they can find signatures of the critical point. So the relativistic heavy ion collider collide at different energies from 200 to 3 GeV. The big question is that can the critical point be identified in the QCD phase diagram? And if so, where does it lie? So here I tell you what happens in hydrodynamic simulation. Basically, they accelerate heavy ions like gold, or lead, close to the speed of light, and when they smash them, so when they accelerate, they undergo through Lorentz contraction and they look like pancakes. So in the early stage dynamics, so the quark-gluon plasma start to form, and in the hydrodynamic phase, so you have the quark-gluon plasma formed. And when the system expands, it starts to cool, and when it cools, it forms, it goes into a process called particularization, where the fluid changes into particles, and these particles stream freely to the detector, and that is what is detected from these experiments. The theoretical interpretation of matter that comes from this experiment is basically hydrodynamic simulation, where they simulate the evolution of this fireball by solving these conservation equations. For example, the conservation of the stress energy tensor and the conservation of the baryon charge, or the charges that you are interested in. So the stress energy tensor, as you can see here, it depends on energy and pressure. So this energy and pressure comes from the equation of state. So the goal of my work is basically to supply the equation of state into this hydrodynamic simulation, and this hydrodynamic simulation should be able to interpret matter that comes from the experiment. So it is always important that the equation of state that you give has some interesting features like the critical point, and also it should be able to cover the region that is interesting, or the region that is probed by the experiment. So let me start by telling you the equation of state at zero chemical potential. So to solve the equation of state, basically we would want to solve this partition function with the QCD Lagrangian. But in this regime, as we saw that the system is non-perturbative, so we cannot solve it. So what happens is that we use lattice QCD, where we discretize the QCD Lagrangian into the space-time. We put the quarks on the sites, and we put the gluons on the link that join the sites. So the partitions in space fixes the volume, and the partitions in time fixes the temperature. So in that case, you are simulating a finite box at a given temperature, and in that case, you can compute all the thermodynamics. But you can reduce this partition function by integrating over the quark fields and doing this transformation. It gives you this relation with the determinant. So it happens that this equation still, it is not easy to solve. What is always done is to do Monte Carlo sampling or importance sampling by treating this quantity as a probability weight and then do importance sampling. But when the chemical potential is 0, we can do the simulation. But when the chemical potential is non-zero, importance sampling is impossible. So in that case, because the probability, this quantity becomes complex, so you can no longer treat it as a probability weight. So, and this is what we call the Fermi sign problem. Some of the way out, you can already simulate at imaginary chemical potential where you don't have the sign problem, or you can do expansions around mu b equals 0, and you're able to find the equation of state. So my work basically is to do expansions around mu b equals 0 to try to find the equation of state at finite mu b. So these are the results of the at mu b equals 0 of the equation of state at mu b equals 0. So the red is the pressure, the green is the entropy, and the blue is the trace anomaly. And these were computed from 2 lattice collaborations. So these results come with errors from systematic errors and also statistical errors. Because since you do discretization, you need to push to the quantum limit, and also you need to do the thermodynamic limit, and also you need to approximate to the physical quark masses. So in the first part, I will discuss the equation of state at mu b equals 0. So using the result at mu b equals 0, the standard way of pushing the equation of state basically is to use the tidal expansion, where you expand, where the pressure is defined as mu b with the expansion parameter mu b over t, and the coefficients are computed on the lattice. The coefficients, these are the derivatives of the pressure respect to chemical potential at 0 chemical potential. In principle, to compute the pressure, you need infinite coefficients, but I'll tell you that these are the coefficients that are available from the lattice. So we have chi2, chi4, chi6, and chi8. And to compute each of these coefficients, I'll tell you that it takes about 2 years to compute in a supercomputer. So we are limited in the number of coefficients that we can have. But still, this tidal expansion works well until it doesn't. For example, as you can see from these coefficients, so the error bars become larger, so it becomes hard to extract the signal. Also, if you use these available coefficients to compute the thermodynamics, so this is chi1, which is the baryon density as a function of temperature for different orders in expansion. The red is the leading order, the green is the next to the leading order, and the blue is next to the leading order. If you see at mu b equals 0, if you see at mu b over t equals to 3, chi1, or the baryon density as a function of temperature, next to the leading order, we have these unphysical behaviors. This unphysical behavior is due to the truncation of this tidal expansion. So in that case, tidal expansion is limited to mu b over t equals to 3 when truncated up to order 8, despite the computational power. And also, it was observed that including one more order into this expansion does not improve the expansion. What was done recently by the UPATA Budapest was to simulate at imaginary chemical potential where there is no sign problem. And it was observed that this quantity T chi1 as a function of temperature for different values of imaginary chemical potential, when shifted with a constant quantity kappa mu b over t, the lines fall on top of each other. And this looks exactly like chi2. So these chi's basically are the derivatives of the pressure with respect to mu b, and these are the coefficients that appear in the tidal expansion. So this T prime expansion scheme basically relates chi1 to chi2 through temperature T prime. When it is fitted to a function, you can always write it as an when it is fitted to a function, you can always write it as an expansion with new coefficients, kappa, kappa 2, and kappa 4. So also, we know that chi1 at mu b equals 0 is 0. So if you put mu b equals 0, so you have 0 over 0, which requires you to take the derivative. And at mu b equals 0, this identity is consistent. But also at finite mu b, you can always find which coefficients correspond to that. And from the lattice, these coefficients are calculated. So kappa 2 is the one in blue, and kappa 4 is the one in red. We see that kappa 2 is fairly constant in this region where you expect the transition. And also, there is a separation between kappa 2 and kappa 4. Kappa 4 is consistent with 0, and there is also good agreement with the HRG, which is the low temperature description of the phase diagram, as I'll explain in future slides. Yeah. Yeah. That's what I'm going to show in the next part of the talk, where we discuss the convergence properties of the T prime expansion scheme. So here I've not talked about how much we can push it. We don't know yet. Because you're only yeah, yeah. Yeah, for now, I'm just motivating the T prime expansion scheme. I'm going to talk about what are the limitations of the T prime expansion scheme. Thank you. Okay, so later in the work by the lattice collaboration, it was observed that, so what I showed you were basically expansion in UB. It was observed that when include heavy ion conditions, which are the strangeness neutral, this shift no longer works, or the relationship between chi1 and chi2, especially for temperatures about 200, as you can see, the different lines of different imaginary chemical potential, they don't fall on top of each other. So in this case, what was done was to correct the high temperature limit by dividing the equation chi1 by the corresponding Stefan-Boltzmann's limit, and chi2 divided by the corresponding Stefan-Boltzmann's limit. So this redefines the T prime with new coefficients, which we call lambda, which are not the same as the one I showed earlier for kappa. And by doing this, it guarantees that your identity or your expansion scheme follows the correct Stefan-Boltzmann's limit, as you can see here. So what are the advantages? So the advantages are that we have the equation of state at finite density that uses fewer terms, and it is compatible with the correct Stefan-Boltzmann's limit, as you can see. Is someone online? Okay, so also in tide expansion, we expand at a constant temperature, but here we expand with a quantity that has a mu b dependence, and this can reproduce the QCD transition line, which we see that it has a curvature. Sorry, someone online? Someone should mute. Okay, so the aim of my work basically is to test the convergence properties of this T prime expansion scheme. Hopefully it will answer your question. And another one is to include the critical point into this T prime expansion scheme. And the next part is basically to extend it to 4 dimensions. So in this part, what we want is to test the convergence properties of the T prime expansion scheme. So what we do, we compare the baryon density from the tide expansion scheme, from the T prime expansion scheme, and the T prime expansion scheme with the Stefan-Boltzmann's limit. We compare the coefficients at the same order, and in that case, we can find what are these kappas in relation to the coefficients of the tide expansion. So the blue are the coefficients of the T prime expansion scheme, and the red are the coefficients of the tidal expansion scheme. So we derive this relation by matching order by order. And we see that kappa 2 is related to chi 4, and kappa 4 has a relation with chi 6, which is at a higher order compared to the tidal expansion. We did the same also for the T prime expansion scheme with the Stefan-Boltzmann's limit, and we got this relation. So the goal here is basically to test how many orders do we need in tidal expansion compared to how much we need in the T prime expansion scheme, and we see which one approximates better. So in that case, we use the HRG model for the low temperature, and also we use the cluster expansion scheme model for the high temperature. These models are interesting because we can compute quantities analytically compared to other models. So this is a choice that we made. So basically, tell you about the HRG model. In the HRG model, basically, you approximate hydronic interaction by creation of resonances. Basically, you have a non-interacting gas of hadrons and resonances, and you can construct a grand canonical ensemble, and the ideal pressure looks like this, basically using Fermi statistics. But in this case, we use the classical pressure or the Boltzmann's approximation when this eta equals to 0. But also eta can be either plus or minus for either if you treat them as bosons or mesons. Bosons or baryons, or fermions and bosons. So then we solve these. So this is the ideal case where you treat particles as point-like. You have no interactions, no attraction, and no repulsion. But when you go to higher densities, interactions become relevant. So in that case, you need another model, which is the excluded volume. By solving these equations, where A equals to 0 and B equals to 1, it is fitted to the lattice. So the excluded volume models basically the repulsive interaction. You treat basically hadrons as non-point particles, but with a given volume. When you go to higher densities, van der Waals or attraction and repulsive become important. So in that case, you use the van der Waals where the parameters are fitted to the nuclear liquid gas model. So before we discuss the convergence of the expansion, it is always important to talk about the radius of convergence of any expansion that you have. So the radius of convergence, basically, if you use the simple D'Alembert formula or the ratio test where you take the previous order divided by the order before, you can always find the radius of convergence. But also these models where you can have analytic functions, the radius of convergence is limited by the singularities in those functions, or it is the distance from the center up to the first singularity in the function. And it can be given by solving this equation. And for the ideal case, the radius of convergence is infinite. We don't have interaction. What does that mean? It means that you need infinite coefficients for you to approximate the exact. So the exact is the one that is in a solid black. So the red is the lowest order, order 2, order 4. The blue is order 6. So each order you add into this expansion approximates better the full result. And you need infinite of them for you to approximate the full result exactly. But also, if you look at the models where you have interactions, for example, the excluded volume, the radius of convergence is given by this expression, and the van der Waals, the radius of convergence is given by this expression. So for the excluded volume, you don't have a critical point, but you still have a critical point in a complex plane, which limits this radius of convergence. For the van der Waals, it is basically the nuclear gas critical point that limits the radius of convergence. So here, if you look at the plots of the baryon density as a function of mu b over t for different orders that we add, the solid black is the exact result. So we see that below the radius of convergence, especially for the van der Waals, below the radius of convergence, the next order you add approximates better the full result. But above the radius of convergence, they don't, they just diverge. So that is expected because that's what the radius of convergence does. This is well understood basically in a tiled expansion, but if you go to the T prime expansion scheme, the radius of convergence is not trivial because it's not just a simple power series. So in that case, what we do is basically to compare the results that we have from the tiled expansion. The radius of convergence, I forgot to tell you, it is basically the solid, the dotted black line, as I showed there. So what we do, we compare the tiled expansion and the T prime expansion scheme in the HRG model, and we check how many terms do we need to approximate the full result, which is in the black. So here we see that for the ideal case, there is not much advantage of the T prime expansion scheme compared to the tiled expansion. But for the excluded volume and the van der Waals, still we see that the dotted black line is the radius of the convergence of the theta. As I said, we don't have a radius of convergence for the T prime expansion scheme. We see that still below, the next order approximates the full result compared to the orders below, but still they diverge above the radius of convergence. So what do we see? We see that there are no significant advantages over the tiled expansion. There are no significant advantages of the T prime expansion scheme over the tiled expansion in this low temperature regime. And also, if you do the Stefan-Boltzmann's limit, which I don't show here, the T prime expansion scheme with the Stefan-Boltzmann's limit doesn't improve the results. And that is expected because the HRG model is a low temperature regime, and the T prime with Stefan-Boltzmann's limit is expected to work better at high temperature. So what we did also was to test in the cluster expansion model, which is a model that works at high temperature. So in the cluster expansion, basically the grand canonical partition function, instead of expanding in mu b over t, we expand in fugacities. So, and in that case, the baryon density can be given as a Fourier series given by this expression, and the coefficients are basically the inverse Fourier transform. This model is interesting because it preserves the QCD, Roberts-Wise periodicity, or where mu b is given by mu bi times pi t, and in this case, it is a model that is relevant. So these coefficients basically can be fitted to the lattice and the correct Stefan-Boltzmann's limit, and also for the low temperature, it was the excluded volume model used in this reference. So the most interesting thing is that from this model, you can always find the analytic structure, which is given by this expression. So it happens that you don't need all the coefficients. What you need are basically the first two coefficients, and then you can form the analytic structure where the baryon density is given by this expression, and these Li, these are the polylogarithms given by this expression here. So as we saw that the radius of convergence is the distance from the center up to the first singularity. So the radius of convergence of the cluster expansion are given by the first singularity in a polylogarithm given by this expression here. That depends on the first two coefficients. So at t equals 200, we can find the radius of convergence is basically a function of temperature. This t equals 200 is interesting because it is the radius of convergence is approximately equal to the Roberts-Wise critical point, which is expected in the QCD. So if we plot baryon density as a function of mu b over t for different orders in expansion, we see that in tiled expansion, below the radius of convergence, we still have what we expect that the higher orders approximate the full result, and above they don't, they just deviate. But in a T prime expansion scheme, if you look at least next to the leading order, we see that it is more closer to the full result compared to what we have in the tiled expansion, even at higher mu b over t. And also, the low order doesn't approximate well the Stefan-Boltzmann's limit. But if you look at the T prime expansion with the correct Stefan-Boltzmann's limit, all the orders approach the correct Stefan-Boltzmann's limit. Mm. Mm. Yeah. Yeah, so here I'm showing them at just at a constant temperature. But the most interesting one is when you look at different temperature. So the question is to look at, yeah, yeah, it is the same but for different temperatures. So if you look at different values of mu b, in tile expansion, we have these unphysical wiggles. So this is baryon density as a function of temperature. So the left plot is a tile expansion, the middle plot is a T prime expansion, and the right plot is basically the T prime expansion is the Stefan-Boltzmann's limit. So in a tile expansion at mu b over T equals to 3.5, we have these unphysical wiggles that we see. And these unphysical wiggles are at least suppressed in a T prime expansion scheme. However, we still have wiggles here. But the most important thing here to see is that if you go to fewer orders, you are already approximating the full result. So if you look at next to the leading order, the purple is more approximating the full result compared to what we have in this expansion. So this expansion doesn't work well with more orders, but with fewer orders, you already have a better convergence. So let me go to the summary of this part. So what we see is that if you look at the second coefficient, which is kappa in the T prime expansion scheme, it is related to chi4 and chi2 through this relation. So here we see that within this region where we have the chiral transition, kappa 2 is fairly constant in this region. At low temperature, it is monotonically increasing. So if kappa 2 is constant, then we have a relation that chi2 is proportional to chi4 through this equation. And this gives us this identity, chi2 prime basically is a derivative with temperature. So it gives this scaling behavior, which is true in the vicinity of the chiral phase transition at mu b equals 0. And also it is approximated or it is preserved for the physical quark masses. So if a model does not preserve this scaling, this T prime expansion scheme is built basically with the idea that kappa 2 has to be fairly constant in the regime that you are interested in. And if it doesn't, like in HRG, the model does not perform well. But in the cluster expansion, we saw that it performs better because in the cluster expansion, it preserves at least that region that you are interested in. So now we have an expansion scheme that can go to higher temperature. In the next part of the talk, basically, I'll discuss how we introduce the critical point into this T prime expansion scheme. So the idea here is to use universality argument. So it is conjectured that if the critical point of QCD is to exist, then it should be in the 3D Ising model universality class. What does it mean? It means that we can map the critical exponents from 3D Ising model onto the QCD, and this is only true close to the critical point. So here I show you the phase diagram of 3D Ising model, where the critical point sits at R equals 0 and H. R is the reduced temperature, which is basically T minus Tc over Tc, and H basically is the external magnetic field. So if you have a magnetic system and you heat it up, you may change its magnetic properties, or if you apply external magnetic field, you may change its magnetic properties. So what we did was to develop was to develop a map. Since we don't know where the critical point is, so we developed a map with 3 parameters that a user can tune and change the location of the critical point. Basically, we map R, or the reduced temperature, to temperature, and the external magnetic field to mu b. And in that case, we use a linear map in temperature and a quadratic map in mu b, where we want to follow the QCD transition line. So this map has the 3 parameters that are indicated in red, and these 3 parameters have a meaning. So TC is basically TC and mu BC. This is the location of the critical point. W can control the size of the critical region, and rho and alpha 1, these ones can control the shape of the critical region. And we compare our parameters with the best collaboration parameter, which is the beam energy scan theory collaboration, where the linear map was used in that case. So this is how our map looks for the choice of some parameters. So this is the 3D Ising model. The black dot is the critical point, and the red is the line of first order phase transition. When we map it onto the QCD, we see that we have 2 critical points. Actually, these are inbuilt in our mapping because it's quadratic. The critical point at positive mu b and the critical point at negative mu b, which correspond to both particles and antiparticles, because QCD has to be symmetric in exchange of particles and antiparticles. So now we know how to map physical quantities from 3D Ising model to QCD. So the next part I'm going to show you is how we introduce the critical point into the T prime expansion scheme. Yeah, we choose the parameters. Yeah, so here, yeah. So here I choose it to be at 500. Since we don't know, we have a freedom. So before, let me start by showing you what was done recently by BEST collaboration. In BEST collaboration, they used the Taylor expansion equation of state, and they introduced the critical point using the same universality arguments by separating the baryon density into the term that has the critical point, which is the Ising, and the term that doesn't have, which is the non-Ising, such that the coefficients chi1 Ising is the one that is the critical point from the 3D Ising model, and the non-Ising reproduces the lattice at mu b equals 0. In this case, they were able to get the baryon density as a function of temperature, and we see, due to the limitation or to the truncation of the Taylor expansion, so there are these unphysical wiggles that I showed earlier. They limit the model of the T prime expansion scheme for the choice of some parameters. In that case, if you want to explore the QCD phase diagram, if the critical points exist at a higher chemical potential, then this model won't be able to describe the critical point. It is limited to mu b over t equals to 500. So in our model, if we merge HRG and also using universality argument, I will show you that we will have an equation of state that can go up to 700, which is higher than what was introduced by the BEST collaboration. So the way we introduce the critical point using the equation of the T prime expansion scheme, the baryon density is chi1 that is related to chi2. So we introduce the critical point by basically separating T prime into the term that has the critical point, which is T prime critical, and T prime that doesn't have the critical point, which is T prime non-critical, and such that these at mu b equals 0 or at some expansion, they can reproduce the T prime that I showed earlier from the lattice. So what we see, so here I show you a plot of baryon density as a function of temperature for different values of mu b over t. So the solid line, this is our equation of state, and the band, these are the extrapolated lattice result up to mu b over t. Okay. So what we see here, we see that for the choice of these parameters, okay.
Yes, so for T prime, that you have there, the sum of these two T primes in different regions. Am I to understand that if you're in the non-critical region, the red part is zero and vice versa? I was trying to understand how to use this blue and red decomposition here.
Yeah, that's the goal. If you are in non-critical region, the critical part basically has to contribute more in the critical region, especially which is controlled by the parameters.
Yes, so you basically, I guess you would say, I don't know, maybe that's a constant or zero in the non-critical and vice versa. Is that how you use this, or?
Yeah, I think it is something that dies out as you go away from the non-critical region. So if you,
Correct. Okay.
yeah,
Okay. Yeah. So that's what it is. Okay.
okay,
Thank you.
yeah, thank you for the question. So here, as I said, that the solid line is our equation of state, and the band is basically the extrapolated lattice result. So at finite UB. So what we see is that for the choice of those parameters, our equation of state, this is so the critical point is put at 350 MeV. So this side you have a smooth transition, and you have a line of first order phase transition, which doesn't introduce new dynamics from the lattice result. So from that, we put the critical point higher at 500 MeV. And in that case, so here I show you the baryon density as a function of temperature and chemical potential. And we see that the critical point is at 500, and this is a line of first order phase transition as we expect. On this side, I show the baryon number susceptibility, which gives you information on how the baryon density behaves when you increase the chemical potential. It reacts with a divergence at the critical point, which is the future that is expected. So from baryon density, we can do just a simple integration to get the pressure. So here I show the pressure. I show the entropy, which is the derivative of the pressure respect to temperature. And here I show the energy density. Also, the critical point is at 500. And this is the line of first order phase transition, or a discontinuity. So the speed of sound is expected to go to zero at the critical point, and this is the future that we see in our thermodynamics. So I showed you that we have these three parameters from the mapping that are indicated in red, but it happens that we can constrain them with the knowledge of physics that we have. For example, lattice QCD, this favors the critical point to be below 450. So in that case, the user can choose not to choose those parameters. Also, in our model, when the user chooses the location of the critical point, it fixes the critical temperature, and also it fixes alpha 1, which is the slope of the transition line. So there is work that was done by these authors, and it was discovered that these mapping parameters can be related to the physical quark masses, and by a natural choice, alpha 1 can be given as the slope itself. Alpha 1, 2 is the angle between the two axes after mapping. So in that case, we are left with two parameters, W and rho. These ones can be fixed by basically requesting stability and causality of the equation of state. And in that case, here I show a map of W and rho. So the red points, these are the points where the equations of state are unstable or are not valid. And the blue, these are the points where the equation of state are valid, which means that they satisfy the constraints that are put by the knowledge of physics. But also, these are not the only constraints, so other constraints can be introduced. So to summarize this work, we developed an open software that is within the Muses collaboration, and it is available online. So the user can download this software and then change parameters, develop equation of state, feed them into hydrodynamic simulation, and then compare with the experimental results. We are almost there. So in the last part, I will discuss the four-dimensional equation of state, or the generalization of this T prime expansion scheme. I've been telling you that the phase diagram is given in temperature and baryon chemical potential, but it happens that we have other conserved charges. For example, we have strangeness and the electric charge. So it is necessary to have the four-dimensional phase diagram. But let me tell you why it is important to have a four-dimensional diagram in temperature, baryon chemical potential. Mu Q is basically the electric charge, and mu S is the strangeness. So in heavy ion collision, from this work, it was observed that the hydro cell fluctuate in both mu Q, mu S, and mu B, even at LHC energies. So it is necessary to provide an equation of state that has all these chemical potential that can be varied independently. For the case of phase transition, it is also important to ask questions: how does the phase structure or the phase boundary shift when you go to different chemical potentials? So, for example, here we don't know how the critical point will behave. In US, it could be extending like this, or we don't know. That's what we are trying to find, and it is important to have a four-dimensional equation of state if you want to model such structures. For the part of cosmology, there is work that is where people study cosmic trajectories, which discuss about the evolution of the universe. And in that case, the baryon chemical potential and electric charge, these are important in studying cosmic trajectories. For the case of neutron star, it is important to have asymmetric matter content, which still require a four-dimensional equation of state. The equation of state is on high demand. So in this work, I'm going to discuss how the previous people developed the four-dimensional equation of state. Basically, these authors developed the four-dimensional equation of state using the Taylor expansion by expanding in the three dimensions of the chemical potential in mu B, mu Q, and mu S, and the pressure is given with three expansion parameters, and these coefficients are computed on the lattice. This equation of state works well. However, as we discussed, the Taylor expansion has limitations, so it is limited to mu B over T in 4 directions up to 2.5. As you can see here, these are basically the isotroms or lines of constant entropy per baryon, so they only go up to 450 MeV. So in this work, we use the T prime expansion scheme that can be pushed to higher values of chemical potential, especially in the region that we are interested in, by basically using a simple spherical coordinate idea. So in this case, we map the Cartesian coordinate of the free chemical potential, mu B, mu Q, and mu S into the corresponding spherical coordinates, like having the generalized chemical potential, which has 3 chemical potential, and also having this angle theta and phi. So what do we achieve by doing this? We achieve that we are just using the 2-dimensional T prime expansion scheme. We promote it to 4 dimension, but what we are doing basically at a constant temperature and constant theta and phi, we can have these 2-dimensional trajectories in a given direction that we want, and we can scan all the phase diagram to have a 4-dimensional equation of state. So the way we do it, we use this 2-dimensional, which was promoted to 4-dimensional, but is basically at constant temperature and also at constant theta and phi. But instead of having these as x's or as chi's, we call them x's. So x's, basically, we call them generalized susceptibilities, which are the derivatives of the pressure with respect to the generalized chemical potential, which is the chemical potential that has all the 3 directions. These generalized chemical potential, we can relate it, these generalized susceptibilities, we can relate them to the normal susceptibilities, like x2 is related to chi2 through an equation, and also x4 is related to these chi-4s through a given equation. And from there, we can compute lambda, which is the generalized expansion parameter. And when we feed it into this equation, we can compute T prime. And when you put T prime into this expression, we can have the generalized charge given by X here. So here I show you the generalized charge for a given direction, theta equals to 45 and phi equals to 45, which is the direction where mu s equals to mu q and mu b equals to, and is equal to mu b over the square root. We see that we can push it up to mu b over t equals to 3.5. This is the charge against as a function of temperature for different values of mu b over t. So from the charge, we can integrate to get the pressure in a given direction. So we fix the angles, theta equals to 45, and we can get the pressure in that direction. And the entropy is basically the derivative of the pressure with respect to temperature. So I'll conclude. So in conclusion, let me hope that I was able to convince you that the T prime expansion scheme covers a larger density compared to the conventional tide expansion, and it can push the result to higher chemical potential. And also it works well in models, especially that preserve this relation, which is the relation that is true for the in the vicinity of the Cairo phase transition. And also in my work, we were able to develop an open software that uses T prime expansion scheme and universality argument to give the community an equation of state with a critical point from the 3D Ising model with a reliable density coverage up to 700. And also it is higher than what was covered by the tidal expansion, which was limited to 450 MeV. So here, as I showed you, the result from the best collaboration up to 450, and we have the baryon density that can go to a higher chemical potential up to 400. And our results can be, has an interesting feature. It has adjustable parameters that can be used by a user and put them into hydrodynamic simulation in order to compare with experimental results, especially from the beam energy scan, which has completed data taking. In the last part, we have generalized the T prime expansion scheme to give a 4-dimensional equation of state with a reliable density coverage. So this is also available. It can be used by the user in order to do statistics, and the hope is to introduce the critical point into the 4-dimensional space. So these are the achievements, the publications that I've acquired during my stay at University of Houston, and these are the open softwares that we're able to develop, and they are available in the MUSES collaboration framework, which is the framework that has most of the equation of state. In that case, other users can use them and merge them with other equation of states that describe different ranges. So these are the presentations I've given, both national and international conference, basically excluding Mexico. But it was online. So thank you for your attention. And I would end with some of the important words from someone wise whom I don't know. Education is the key to success.
Great talk.
Thank you. What is additional phase transition? 160? It's not a phase transition. No, it is just so it could be an artifact. Also, it could be for the choice of parameters that you have. Some parameters could behave more strongly, but no, it has no physical meaning. Two. 32. I don't think it's 32. 27. This? Oh, this one. Mhm. Mm. So one of the reason is that each point you choose W and rho and then compute the equation of state and you check stability. So the way you check stability, you check if the speed of sound is between 0 and 1, and also you need to check the susceptibilities are positive, and you need to check that CV also is positive, the specific heat at constant volume. So in that case, each point you have to compute the equation of state. So it is time consuming for you to have a continuous stuff or to compute all the points, because each point you have to run the code that takes some time to compute. So this plot, it takes time. So if you are to use, yeah, so you cannot have a color plot. So you have to make a choice. And where there is a boundary, it is interesting because you don't want to show a plot where you have only rays. So you keep checking in the equation of state. You change parameters and then yeah. Yeah. Yeah, but you need to compare with the experiment. So me, I don't predict. I just give a tool that gives equation of state. So for you to know which equation of state is better, you need to know what the experiment has to give. So you have to feed all these equations in hydro and then see which connects better to the experimental results. Rutik. Mm. Mm. I didn't understand the question. Yeah, yeah. Mm. 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 Yeah. I think I think we are misinterpreting. So this is just the equation of state. So for you to compare with experiment, there is a bridge which is hydrodynamic simulation. So from hydro, if you can give me the equation of state, or if you do the experiment, then if you can reverse the hydro, then I can see which parameters match what you want me to see. But there is a bridge which is hydrodynamic simulation, which compares to the experiment, and it takes in the equation of state. So maybe we can discuss more about that. Yeah. Okay. Thank you. Oh, yeah, we still have questions in the room. Maybe we'll get back the people online.
Okay, I have one question.
Okay.
Lovely talk, very impressive results.
Thank you.
In the last, the treatment, the 4D treatment, you cleverly used spherical coordinates, and then by restricting yourself to the radial direction for a fixed direction,
Yeah.
an array for a fixed direction, then you were able to use the 2D stuff that you had done before, right? Basically, so that's very
Yeah.
clever. So, and you had chosen for this example, I guess, 45 degrees or something like that. So,
Yeah.
how's why do you choose that direction? So, or broadly, you expect. So, do you want to probe, or did you probe other directions, or is it necessary, or what? I would assume that it means something. Otherwise, the extra charges would be just kind of riding along for the ride. So, can you say something about that?
Yeah, I think the main choice of the direction was to make sure that at least we have all the three conserved. So we chose a direction where all the three conserved charges are, are, are available. And that was direction theta equals to 45 and phi equals to 45. But yeah, but different directions dep depends on the physics that you want to probe in that case. So also in the mu b direction, that is what always people use, but also in the strangeness neutral, you can choose the direction where the charge is 0, and then or where the the where you only have only two chemical potentials and preserve the conditions that you want to have, like strangeness neutral. Yeah.
Thank you.
Thank you. Yes, sir. Mm. Yeah, so for the first question, so here in HRG model, basically you treat interactions as creation of resonances. So instead of these hadrons or protons and neutrons interacting to each other, you you look at it as basically a non-interacting gas of these hadrons and resonances. Resonances are basically excited states of these particles that you have into the system. So for the Stefan Boltzmann's limit, what was the question? Yeah, 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 yeah. Yeah, in this physics, basically, we are looking at high energies or at high temperatures. So if we talk about the low temperature regime, it is low to us because we have higher stuff compared to that. So the Stefan Boltzmann's limit, according to the quantities that we are looking at, it is still high. So the the expansion, I don't know how to explain it to you. Maybe we can talk after. Yeah, it's a bit, yeah, yeah, yeah. Yeah, that's why actually at the beginning I talked about the four forces of nature. So we have the weak force, the strong force, and the electromagnetic. But here, the Stefan Boltzmann limit is still far. So for the people online, I think you have to leave apart from the committee members. Thank you for coming.
Very nice talk.
Thank you, Joaquin.
Good job, Michael. Yeah, good. Very good talk, Michael.
Thank you.
Good luck.
Thank you. No, if you want. Okay. Okay. Yeah, it's my phone. Other people online, you have to leave, except the committee members, Dr. Carlos, and people online, you have to leave.
And you need them?
Can I? I don't know. Okay. Yeah.
Okay.
John, you have to leave. Gabe, you have to leave. Okay. John, you have to leave the meeting. Okay, Gabe is, I think, I don't see. Gabe is not leaving. Yeah, it's our Gabe. Oh, Gabe, you have to leave the meeting. Yeah. Thank you. Thank you, Gabe.
I can't hear you very well.
Oh,
Maybe you can get the computer closer or something.
yeah, let me get the computer
Okay.
close.
Yeah, I was just saying that
Okay, there.
we can ask more questions now.
You
from the
see, I made you
committee.
exercise. That's good.
And Rene goes first. We start from the people in the room.
Oh yeah. Well, thank you.
Okay, no, so let me understand. Oh, let me close. Let me understand the validity of expansion once and for all. Say you're expanding UV over T. It's two numbers, and then you plot against T and you plot against UV. So let me really figure this out. So you have a critical point, 700 MeV UV, and temperature of 100 MeV. Just put a critical point. In order to be able to describe that critical point, you would need to expand UV over T to 7. Is that correct? Correct. Okay. So once you need to quote your numbers in the relevant way, because now there's a plot where you say you are your T expansion scheme is valid up to 700 MeV. T expansion scheme is valid up to 700 MeV if the temperature that relates to that 700 MeV is 200 MeV. Nobody claims that there's a critical point at 200 MeV. So I'm trying to just make sure that we understand. What I misunderstand is that you only can expand to the level where you actually have a point. Yeah.
So you do it 500 MeV and 115 MeV, and that comes out to about 150 MeV. That comes out to about 3.5, and that's pretty. But then you cannot claim that you go much higher than that.
Yeah. So what we say is that it gives, so what we match basically they are three stuff. So we have the low temperature limit, which is HRG. We have this T prime expansion scheme, and we have the critical point. So the critical point, only its physics is more relevant around that point, but we see that it doesn't, combining these three structures does not introduce new dynamics into our equation of state. So in that case, up to 700, we still get reliable results. Like we don't have these unphysical wiggles.
So you call it, but then you call it a validity range, and then so it would have a critical point at 700 MeV. It would definitely not have a temperature.
Yeah.
So you're outside of the validity range for that critical point.
Yeah.
What you're saying is you don't see a wiggle in this range.
Yeah.
I think this needs to be quoted properly. Okay, there needs to be a mu b and a t, because you're expanding in mu b over t. Because it becomes always confusing that you're expanding in the one and leave the other one free. So I'm not so sure, because in particular by pointing out that expansion only goes to 50 and then the other one goes to 450, the other one goes to 700. Maybe those two numbers are in agreement relative to some temperature, but I don't see that temperature. I don't know what temperature I should be. I think that's a general problem for me, because if I look at a QCD phase diagram, first look at the temperature. And the mu b is relatively trivial, but the temperature evolution is not linear. It is pretty constant, and then it starts to drop at some point, maybe in a very relevant region of the phase diagram. So you need to find a way to connect those expansion scheme, the validity of the expansion, and the point you actually make. So the other question, I only have one more. The other question that I have is this cluster expansion. So now so we all understand that HRG is used at low temperature, and you can apply it. And I think realistically, one should apply it up to and then one should stop applying. So now, maybe with excluded volume and other things, you can push that to a higher temperature, but then you also get into the region that you start to describe as quark-gluon plasma with a hadron resonance. That was not the purpose of it. So now you're trying to describe a quark-gluon plasma with a cluster expansion. There are no quarks and gluons.
So the cluster expansion, it uses lattice result. So basically, you have a Fourier transform. Instead of expanding in mu b over t, you have a Fourier transform with the coefficients. So these coefficients are fitted to the lattice result. So the quark-gluon model is basically the lattice model. So you fit this expansion at mu b equals 0, but the expansion is a cluster expansion. So the reason of using it, because you can always have the analytic form of this expansion, and you can compute things like radius of convergence.
So the cluster expansion is clustering quarks and gluons in the lattice QCD.
Yeah. It's fit to the lattice. It's like tide expansion where you have coefficients, you fit these coefficients to the lattice. So cluster expansion is another, I can show the slide. Let me keep the presentation. So this is the expansion. So you expand in exponentials of mu b over t, and the coefficients that you have, you can always relate them to the susceptibilities or to the coefficients of the lattice. And if you fit these coefficients to the lattice, then you get an expansion. but you are expanding, instead of mu b over t, expanding fugacities, which are exponentials of mu b over t. Yeah, actually it is an old work that was done by people earlier and Volodier, and it gave this expansion, but people didn't continue much into this expansion. But the most interesting thing was that this expansion, basically, you just need the first two terms. They are expressions that I didn't show here. If you get the first two terms, you can relate it to a polylogarithm, which is basically an expansion, and you can find the analytic form of this. But what you still need is to fit these coefficients to the lattice. So if you have new lattice result, you have to fit it to the lattice result.
That's the way the real expansion works out. So,
yeah.
But here you feed it to the lattice.
Yeah, you feed it to the lattice, and compared to other models at high temperature, for this, the analytic structure is important.
I think the problem with those
Mm.
you're using a model and then using across the face. That's why you use two models. But in both cases, you actually have the low temperature part in the expansion model and the high temperature model, knowing that you're going to a phase.
We're done. Yeah.
Well, you use it where it works. I mean, self-deviated. It would be nice to see it as a expansion model.
Yeah, so the temperature is 155, which is like what we do.
The expansion model could also fail at the low temperature part.
Yeah, you can not only fit it to the lattice, also you can fit it to the excluded volume HRG, because lattice results are basically within this temperature, 150 to 200 and something. But if you want to go to low temperature, you can still feed this cluster expansion to HRG and you find the coefficients. And then you can describe the phase diagram. Yeah. So if you have results.
Very nice. Good work.
Thank you. Thank you.
Okay, good. First one. So I guess we're trying to figure out a little bit more
Yeah, I think having the critical point into the equation of state is one of the good things to model, like how will the critical signatures be. But still, theoretically and experimentally, it is still hard to connect these two. Like, we need to know what are the beta probes that we need in order to see the critical signature. That's a good question. So the reason why people think that they are critical point, we have QCD effective models. So these effective models predict that there is a critical point somewhere. And also it is interesting that most of the models predict in a region that is close to each other, especially when they are fitted to the lattice result at zero chemical potential. Remember, you don't fit at finite chemical potential, you fit at zero, but then you predict that there is a critical point. So those are theoretical models. Experimentally, people are still searching using the beam energy scan, but it is possible that the critical point could not be there. But if it is there, then it's a good thing. Yeah, this is in equilibrium. Mm. Mm. Yeah, yeah. Mm. Yeah, so I think it depends on the theory that you are looking at. So the hydrodynamic model, they have the models that are like in the ideal where you are assuming equilibrium, but also you can add transport coefficients basically out of equilibrium, like the bulk viscosity. So it is basically a modification of this tensor. So you can add out of equilibrium effects. Yeah, there are corrections to this. Yeah, yeah, yeah. No, yeah, I don't know much about hydro, but what I know is that they sort of, if they are in this hydrodynamic phase, you have a fluid, but there is when a fluid is going to change into particles, then you need another equation that is sort of like the Cooper-Frye equation. So I can't say much about the time scales they use. Yeah. You have Dr. Giribason?
No, I can't really say that I would have anything to add here, so I'm not going to ask a question. No, I don't have any further questions.
Thank you.
Thank you.
Easy. I asked fine.
We are done.
Sorry. Oh, then,
Yeah, now you got to start.